Not every sweep line problem can be solved with the distribution sweeping technique that we saw in the previous video. Sometimes you need to make things slightly more complicated or slightly more advanced. One example of this is this rectangle intersection problem, where given a set of axis parallel rectangles, we want to find all the intersections. To see why this is a bit different, we could try to solve this problem using the previous idea. Like again, we distribute the rectangles into m over b minus 1 slabs with roughly equal number of endpoints in each slab, and then we do the sweep. Okay, so the previous parts are the same. So the recursion part is the same. And again, the main part is how do we take care of the spanning parts. Okay. Now the issue is that it seems difficult to perform the sweep approach that we did in the previous step. This is obviously because in the previous approach we had two types of line segments, a vertical line segment and a horizontal line segment. And a vertical line segment would only go to one slab, whereas a horizontal line segment was the one that we used to filter through them. Here we just have rectangles. We don't have a notion of a vertical rectangle or horizontal rectangle. They're just rectangles. So therefore it's really, we don't have that distinction between vertical and horizontal anymore. The way we can solve this problem is to reduce the number of slabs that we have from m over b to something like square root m over b. The main advantage of this is the following. Let's say x is the number of slabs, right? So this is the number of slabs. In the previous approach, we could have x blocks in the internal memory. In memory. If I take the number of slabs to be square root m over b, I could store x squared blocks in the internal memory. And this is much larger, right? So I could essentially increase the number of blocks I could store per slab in the internal memory. That's the first effect. But the secondary effect of reducing this fan out is actually not very big, because if I distribute the input into square root m over b slabs, then the size of the input goes down inside the recursive call by square root m over b factor, essentially by factor x. And of course, log of square root m over b is the same as log of with m over b, just with the factor 2, which disappears into the O notation. So I could easily afford to reduce the number of slabs from m over b to square root m over b without changing anything in the symptotic running time. So therefore, here I just have essentially, I can have one active list per tuple of slabs. In other words, for every index I and j, so for every I and j, I less than j, I can have an active list from slab number I all the way to slab number j. For example, this will be one active list, this will be another active list, this will be another active list, and so on. And now what happens when I do the sweeping? When we do the sweep and we encounter a rectangle, we put this in the specific active list. We insert this in the active list, in the larger active list that it spans. So for example, this rectangle is placed inside that active list. The active list that goes from this slab to that slab. And the behavior of the active list is exactly the same as before. We keep up to b elements from every active list inside the memory. If I need to insert one more element, if an active list has already b elements, then we write those extra elements to the disk. So therefore, that's the operation that we do when we see the top endpoint of a rectangle. Whenever we see top endpoint, we insert that rectangle in the corresponding active list of a multislab. But we also do something else. When we see this top after doing the insertion, we go through the relevant multislab list to find expired rectangles or to report intersections. So now the interesting point is what are the relevant multislab lists. So let me just show an example. I'll also change the color. Okay, so let's say I encounter this rectangle. I put this inside this active list, and then as I did the previous thing, so now I want to show you what are the relevant active lists. The relevant active list is any active list that potentially could intersect this. So for example, this includes any active list that includes this lab or this lab or both. For example, that is a relative active list, relevant active list. This is another relevant, this is another relevant active list, another relevant active list, and so on. For every relevant active list, so let's pick an example. So let's say for this active list, I go to the rectangles that are inserted in that active list. For every rectangle, if the bottom endpoint of that rectangle or the bottom boundary of the rectangle is above this top endpoint of this rectangle that I just inserted, I will delete that rectangle from the active list because it's expired. But otherwise, if it's like this, then it creates an intersection, so I will report this. So once again, once I go through these blocks of the disk that correspond to that active list, I have two choices for every rectangle that is stored there. Either it will be deleted or it will produce an output. And I could charge this operation of reading this block of elements to either an input rectangle or to an output element. So therefore the asymptotic running time won't be different. So scanning through the multiple relevant active lists can be done in O of n over b IOs plus t prime over b. Well, t prime is the amount of output that I generate with this scan. And that concludes the multi-slab idea.